Hi, my name's Sam, and welcome to our presentation on the inertia of axially symmetric bodies. Today we will be discussing the definition of axially symmetric inertia, derivations of equations related to the inertia of such bodies, and real-world applications of these principles. We hope you enjoy.
For a point mass, the moment of inertia is defined as mass times the square of the perpendicular distance to the rotational axis. This is the basis of all other moments of inertia since they can be broken down into point masses. This can then be written as an integral. We can find the moment of inertia useful for many shapes, but one very useful result is the moment of inertia of an axially symmetric cylinder. Consider a cylinder as shown in the diagram. Now imagine splitting the cylinder into n hollow cylindrical tubes with infinitesimally small thickness, dr, and mass m. Now the equation for density is mass over volume, so for one of the hollow cylinders we get dm over dv, and therefore our dm is equal to rho times dv. And dv is just the circumference times height times the thickness of the tube, which is dr. We now integrate, substituting in our dm and removing constants. We end up with a result of pi over 2 rho z r to the 4. But the total density of the cylinder is m over pi r squared, so substituting this into our equation we get half mr squared. So the moment of inertia doesn't depend on the height of the cylinder, which makes sense when you consider breaking it down into small disks.
When deriving the moment of inertia of a cylinder, we saw that it does not depend on its height, meaning we have a general equation for the moment of inertia of a uniform disk. From this, we can find the moment of inertia for any axially symmetric body by splitting the shape into a series of disks and summing over their individual contributions. So the total moment of inertia is given by this expression. This summation is possible if we consider an infinitesimally thin disk of thickness delta z and radius r of z, as shown here, where the radius of the disk becomes a function of z, so it can vary with height to fit the arbitrary shape profile. If we recall the moment of inertia of a uniform disk and insert it into this equation, we get this expression, where the summation just becomes an integral between the lower and upper height of our arbitrary shape. By considering the equation for density, we can rewrite the moment of inertia in terms of mass. Here, the total volume becomes the sum over each disk's contribution, where the summation is again replaced by an integral. If we plug this density into the moment of inertia equation, we get this expression. When we apply this to the previous example of a cylinder of height z, we obtain the same expression for the moment of inertia. Here, we use the fact that r of z is just the radius of the cylinder.
Moments of inertia have many useful applications in engineering. One example of this is in the construction of axially symmetric architecture, which can be seen in the photo. The moment of inertia can be used to ensure the building is at its optimal performance and is especially useful in ensuring the safety of a construction in natural disasters such as earthquakes.
I will be going in depth into the moment of inertia's impact on bicycle wheels. More specifically, the differences between ring-shaped wheels and solid disc wheels. Here are the expressions for each wheel type's moment of inertia. We can see that the ring-shaped wheel will have a greater value than the solid disc. Thus, the ring wheel resists changes in motion more than its counterparts. However, what exactly does this mean when using these wheels in practice? The ring wheel will initially be harder to move as more effort is required, but will be easy to drive with when it is already in motion. Jerks whilst braking will be less likely as well. Its counterpart has the opposite qualities for everything I've mentioned before. The ring wheel's ease of use is why it is widely used as opposed to the disc wheel, which is more prevalent in sports.
Another use of the moment of inertia of axially symmetric bodies is the flywheel. Flywheels are mechanical devices that store energy in the form of angular momentum. They are designed to have large moments of inertia in order to maximise the angular momentum that can be stored in the wheel. In order to achieve this, they follow a similar design principle to the ring wheel previously mentioned. As shown, the inertia about a hollow cylinder is greater than that of a solid cylinder. Because the angular momentum and therefore the kinetic energy of the system is proportional to the inertia, this ring design maximises the amount of energy stored in the flywheel. The inertia and subsequent resistance to angular momentum of the system means that flywheels can also be used to smooth out mechanical power outputs. As such, flywheels could be described as mechanical equivalents to electric accumulators. Flywheels used in this manner ensure that the power output of the system remains constant despite fluctuations in the input. Flywheels were most popularly used during the Industrial Revolution, where machines would use steam and mechanical methods of transferring energy. They are less common today, where most machines use electrical energy. However, they are still vital in industries that deal with a large amount of mechanical energy. One example is a hydroelectric dam, which has to process a large amount of kinetic energy. Flywheels ensure that the power output of the dam remains constant and does not overload any mechanical or electrical systems it is transferred to. They also store excess kinetic energy and put it back into the system when the power from the turbines lowers. They are also used in cars, where they store kinetic energy from the engine and transfer it into the drivetrain when the accelerator is not in use, which prevents stalling.